In the last class we have seen minimum mode of interfacing, like how when you are trying to design a system, so then how 8086 works in minimum mode of operation, and how 8086 now works in maximum mode of operation. So complete minimum mode of operation is what we have seen in the last class. So now we'll try to see maximum mode of operation is. So as we said in the last class, the 8086 33rd pin, when it is connected to VCC, it works in minimum mode, and the maximum mode of operation can be obtained by connecting this 33rd pin to the ground. So here so you have to choose between minimum mode or maximum mode. Means here the difference is the control signals, the 24 to 31 pins are different. So now if you try to see this thing, now if you try to see the pin diagram of 8086, then here the 24th pin to 33rd pin, they are different. Now if you see here in this case, so now if you see these pins, when just beside of these pins 24 to 30 pin 31, there are multiple functions are written, like when the 33rd pin, now when it is connected to VCC, then these pins will act like this, like the 25th pin is ALE, 26th is data enable, 27th is data transmit and receive, 28th is whether the processor is doing a memory operation or IO operation, it will indicate, and 29th is write bar and hold and hold acknowledge. This in detail we have seen. These are very important functions. ALE is address latch enable. So now when you try to, like when this ALE is used in address and data bus, demultiplexing. So now here if you try to see, without this, that means when you try to connect your memory or other IO devices, then that address should be carried out for throughout the memory read operation or memory write operation. But when you connect this to VCC, so then these functions, and then when you try to connect the 8086 in maximum mode, so when you connect this in maximum mode, the pin functions are different, and there is no ALE, there is no write bar and all. So now what we do is, what exactly the maximum mode is, when the pin 33rd, when you connect it to ground, then it will act like in maximum mode. In maximum mode, what it does is, it accommodates one more co-processor called 8087. So you can connect 8087 processor, co-processor is, right? So you can connect 8086 co-processor in maximum mode. For doing floating point operations, we need this, but at that time, to accommodate one more processor, the pin functions are varying. So the 24 to 31, the pin functions are different. But we need ALE, we need write bar, we need I0 by M bar for doing memory read operation or memory write operation, IO read operation or IO write operation. So we need these things, right? So now how to obtain these things in maximum mode? How to generate these signals like ALE, data enable bar, and data transmitter receive memory operation or IO operation. So how to generate these things means in maximum mode, what happens is the missing control signals are generated by using an extra chip called bus controller. So here we use 8288 is a bus controller. 8288 bus controller is what need to be connected, need to be interfaced. So that is what the difference between minimum mode and maximum mode is. In maximum mode, we are accommodating one more coprocessor for performing floating point operations. But when it is in maximum mode, the pin functions are different. So what we are doing is we are trying to generate these signals by using a bus controllers. So maximum mode is suitable when coprocessor is used. That's what we are saying. So in that case, more control signals are needed, which makes 8086 to run out of pins, and then the control signals will be externally generated. So now what we do is, so these are the minimum mode signals which we are talking about, which need to be generated. And so these are the signals are maximum mode signals. So here you have request, grant, and request or grant bus access control. So this is request RQ by GT1. So request or grant. Then when you are using coprocessor, your coprocessor can use the system buses, address bus or data bus. So then that case, it will communicate with the processor by using these lines. RQ by ZT1. So this is which pin? Now if you try to see 31 and 30, request and grant, ZT0 and ZT1, request or grant. So the coprocessor uses this particular, coprocessor uses these pins, and then it tries to communicate with the processors. And this lock, so this here, once the processor locks, then it will not allow any other things to access its buses. So bus priority lock control is the lock operation. Then the very important is here we have S0, S1 and S2 bar. So this S0, S1 and S2 bar, these signals we use to generate these things. Now if you try to look, here you have S0, S1 and S2. So these three pins we try to connect. Here if you try to see 26th, 27th and 28th, S0, S1 and S2, these pins we try to connect it to 8288 and then we generate. Now when S0 and S1 and S0 are 000, then we try to generate a control signal interrupt acknowledge, which is there with 8086 in minimum mode. And when it is 001, so then reading an IO port. And when it is 010, then writing an IO port. And 100, then memory read. That means, it reads a byte from the memory. 101, okay. Then this is memory reading operation or writing into memory. So instruction fetching and all can be decided by using these status signals S0, S1 and S2. So 8086 uses one more chip, right, which is called bus controller, and 8288, and then it generates a memory read operation signal or memory write operation signal. Okay, this is memory write operation signal, and when it is 111, it does nothing, right? And then 011 means it will stop, halt operation. CPU will halt its operation as. So these signals, which are there with 8086 in minimum mode, can be generated by using S0, S1 and S2 for doing memory operation or IO operation or interrupt acknowledge operation is. So there it is a write bar and all. So write bar in combination with I0 by M bar are used to perform memory read operation or IO read operation or IO or write operation. So these four signals, which are very important, are generated by using this 8288. That is the differences. Then now if you try to see the maximum mode of operation of 8086. So the basic fundamental here is the minimum by maximum pin, the 33rd pin is connected to VCC, and now whether it is in minimum mode or maximum mode, you have to generate clock signal. The clock signal is generated by using 8284. Right, one more IC called 8284 made by Intel, and here you generate three signals. That's what we have seen in the last class in minimum mode. And then you have here, you are using S0, S1 and S2. These two signals you are giving it to A2C88 is one more IC, and this IC output will generate in combination when S0 and S1 and S2 are, when they are different, right? So then when they are, memory read operation or memory write operation or IO read operation, so these signals, these signals, when it is 000, then interrupt acknowledge. So interrupt acknowledge is what, so here interrupt acknowledge signal will be generated is when it is 000. So here the difference between minimum mode and maximum mode is when the 33rd pin is connected to ground, then it uses S0, S1 and S2 lines to generate different control signals, and rest are the same. Here if you try to see memory read, so here I have a RAM. So when it is a RAM, then I can perform memory writing operation or reading operation. So these two lines are connected to memory, okay, in maximum mode of operation. If it is minimum mode of operation, that we are trying to do with the help of this thing. So ALE signal which is generated by using this 8288 is connected here. Similarly, data enable and data transmit, these two signals are generated by using 8288 in maximum mode, and they are connected similarly to your transceiver buffers or latches. Okay, so then this will differentiate demultiplex. So because there is no ALE pin directly available with 8086 in maximum mode, these signals we try to generate by using 8288, which is called bus controllers. It generates ALE, data transmit, data enable, memory read, memory write, IO read, IO write, interrupt acknowledge. So these signals we will try to generate, and we try to interface memories, we try to design a system like this by using maximum mode of operations. So keep in mind, here what we need to do is, you need to connect a clock generator 8284. So you can connect your crystal here, and then you can generate three signals: clock, ready and reset. And you can use 8288 bus controller to generate the signals, so that you can facilitate this operation also in maximum mode. So this is the maximum mode of operation is. The difference is here 8288 comes into picture, which is used to generate your signals like this. When it is 000, then interrupt acknowledge signal is generated by 8288. When it is 001, IO write, okay, IO read, and when it is 010, then IO writing into IO port, and when it is 101, then reading memory, and 110, then writing into memory. Okay, so these are the signals, control signals are generated by using 8086 in maximum mode of interface. So now you can see the same thing here. So here, this is your 8086, then 33rd pin, when it is connected to ground, it is in maximum mode. Then you can use your S0, S1, S2. This is different, the same thing, but in more clarity manner. So S0, S1 and S2, then you can generate these signals by using 8288, and then you can generate data transmit, data enable and ALE equivalent signals here, which you can connect it to memory. Right, for address demultiplexing, and also for buffers and latches, you can connect these three signals. That's what we clearly seen in our last class. So this is the maximum mode of interfacing. So in maximum mode of interfacing, we are accommodating one more coprocessor with the help of 8288 is what the conclusion is. right? So CPU cycle, what had happens, and then 8 to 8 command is what we have seen as. So maximum mode of interfacing now, when we try to see internally what exactly it is done. So then you have your status decoder, then you have a command signal generator in 8288 is the bus controller is. Then here you have clock A enable, and we can use this particular pin, and then you can generate a control signal in internally AAE data transmit and data enable this. This is what internal of 8288. So coming to the maximum mode of operation, here the pins which are available with maximum mode, we should be very careful. So the request grant signals are used by other devices called masters to take over 8088 the system bus to read write into the memory location such as coprocessors 8086 or 8088, both things. Like, so when another device decides to take over the system bus, it will pull. So what happens, this is what the sequence of operation it happens when another device decides to take over the system bus, it will pull request by grant low for one clock period. When 8086 is ready to release, when 8086 is ready to release the system bus, it will use RQ by GT bar as an output to inform the new bus master. At the second low level, one period pulse does this. So that means it grants the permission. Then the 8086 enters a hold acknowledged state until the new bus master is ready to give the bus back by sending a third low level period of pulse input. So this is steps to steps what happens when it does this. And that is about the three pins. So you have just now we have seen S0, S1 and S2 pins which we are using in a maximum mode. There are other two pins also, QS0 and QS1. So this QS0 and QS1 pins provides the information on 8086. So 8086 internal instruction queue. So that means this information is used by 8087 processor. The queue status bits indicates contents of the internal instruction queue according to the following table. When QS0 and QS1, when they are 0 and 0, then queue is idle. When it is 0 and 1, then first byte of an opcode is available in the queue. And when it is 1 and 0, the queue is empty. And 1 and 1 means subsequent byte of an opcode is available in the queue. So the queue status can be known to the 8087 coprocessor in maximum mode by using these two pins, QS1 and QS0. So when it is 1 and 0, the queue is empty. When 0 and 1, the first byte of an opcode is available. When it is 1 and 1, then subsequent byte of an opcode is available. This is what you can try to see using maximum mode. So now if you try to see the maximum mode timing diagrams, so here if you try to see, this is what your clock. So coming to the timing diagram, we should have 4 clock periods, T1, T2, T3 and T4. And here you are using QS0, QS1 and you are generating address. There is no ALU, so you should not draw ALU. So the timing, if you trace the timing diagram of 8086, then here you can find it out, QS0 and QS1. Right, and then the same thing, like it generates ALE, then it demultiplexes the address and data bus here read cycle. Okay, right. So this signal will be generated by 8288. During this time, the address is available, and after that, the data is available. Then you can use a read bar signal if you want to perform a memory read operation. So this memory read operation signal will be issued by the microcontroller. Okay, a read bar, that means a memory read bar is what the signal how we can generate. This is connected to the chip read operation of your RAM. So then, and this DT by R bar which we generated using 8288, it goes low saying that it is in receive mode. So then the RAM, the memory places byte operation, they byte onto the data bus, then that can be read by your microprocessors. So this is the maximum mode of operation and its timing diagram. The difference is here, there is no directly available. So here you are adding up QS0 and QS1 to generate your ALE equivalent signal, ALE signal, and here you have data transmit signal and data enable signal. Okay, and memory read and so this 8288 means if you connect this to CRO, then you can observe these things in maximum mode of operations. Okay, so this is what the minimum mode and maximum mode of operation of 8086. So in minimum mode, in maximum mode, the processor accommodates another co-processor which will do floating point operations. Is it all right? Yeah. So now this is about how you are designing a system, a basic system, and its hardware details regarding 8086s. Right? So now this is what the syllabus of your course. So here we are trying to discuss 8086 architecture and is what we have seen, and now we have seen this minimum mode and maximum mode of operation of 8086. So the hardware connections and then the timing diagrams are very important, how they are in minimum mode and how they are in maximum mode of operation. And coming to the programming point, we have seen the instructions and addressing modes. In the next class, I will be giving you the clear-cut details about, like, by taking 3 to 4 programs, how can you write. So now we started with this interfacing, 8086 interfacing. So now we'll go ahead with this particular topic. So how to interface RAM and ROM to 8086s. Why? Because you are designing a system, a programmable system where you need to add your RAM and ROM. Okay, so now we are going to this third chapter and where we are going to connect memories RAM and ROM to 8086s. So it's very important now, what is this memory interfacing is. So now let us go ahead. Here, what is memory? So if it is a programmable system, if it is a programmable system, this is what your microprocessor, and here you are going to connect your memory to the microprocessor is. So in the last class I clearly explained like what is interfacing is, connecting in a compatible manner. So this memory to your microprocessor is. So this memory can be of RAM and ROM. This memory can be of RAM and ROM. And now how to connect that in a compatible manner so that data transfer can take place from memory to the processor or processor to the memory is what we try to see. Okay. So now why RAM and ROM? Your booting instructions will be there in ROM because it is non-volatile. RAM is volatile but very fast. That's why we need both RAM and ROM. So then this is what your computer memory system, how it looks. So this is what your CPU, and then here you have your main memory and then the secondary memory. So now we are talking about the main memory, how we are going to interface to the things. So an interface is a device or a set of rules that is designed to match the output of one device to another device. So that's what we are saying. Interfacing means connecting in a compatible manner. So now memory interfacing. Memory we need to interface to 8086 processor. Then you know what is the RAM IC available, and then what is the 8086 available, then which pin of this microprocessor will connect it to which pin of my memory is what now we need to see as. So an interface includes a physical connection, and then the hardware details of this one if you have to know, because pin to pin connection if you want to do, then you have to know the hardware, and for that you have to follow a set of rules or procedures. So the connection between the microprocessor and external memory is an interface is what you can consider as. So prior to interfacing, what you need to do is, before attempting to interface memory, it is essential to understand the operation of memory components and memory types. So the memory types can be of, if you consider ROM, that can be ROM, PROM, E square, PROM and SROM. ROM means the contents are written, okay, the contents are written in the contents are written in the while fabrication itself. PROM means the manufacturer give an option, the manufacturer can give an option, you can connect, that means you can buy it and then you can program it once. And E square PROM means electrically erasable programmable random access memory. So you can, in number of times you can write, erase the contents and you can write if you have a flash programmer. So these are the ROM types. And coming to the RAM types, you have SRAM and DRAM, static RAM and dynamic RAM. Okay, so then now if you want to interface these memories to your 8086 processor, then 8086 processor is an Intel make. So your RAMs and all should be given to an address which starts from 00002 E0000 and E002 EFFFFF, which is of 64K, and F00002 FFFFFF is given. This area is for EEPROM connection. Intel follows this structure. The top of the memory is where we connect the EEPROM, and the bottom less than E00, there you can connect your SRAM addresses. So this is what the memory mapping followed by Intel. So now the moment we are saying memory mapping, what we should do is, you have to know when you are designing a system how to configure these addresses, how to give these addresses to the memory, so that when processor gives a address, then address decoder decodes to or selects a particular memory location as, right? So now coming to the memory mapping, giving these addresses starting from 00000 to E0000. So these addresses you should give it to SRAM or DRAM which you are using, and E002 EFFFF you should give it to FF. You have to give it to EEPROM. So how to decode this particular address so that that particular content is identified is what memory interfacing is, right? So here, why you have two different types of memories? Here we are talking about RAM and ROM. But now if you try to see the memory characteristics, memory access time of RAM is very small. Within no time, the RAM responds to microprocessor fastly. But whereas SRAM is volatile, means when the power is off, the content will be erased. So they can be volatile and non-volatile, and modifiable, and density point of view. The packing density is one more word by which we describe the memory. The more number of transistors fabricated or the more number of bits you can save for the given area is what you can consider as. And power consumption is also one important factor in selecting of memories. So if you try to compare RAM and ROM, the memory access time of RAM is less, ROM is more. And volatile and non-volatile is what we try to say, and then the space density is what we try to consider is. So now if you try to consider a RAM and ROM, when any memory interfacing need to be done, then we should know what are the pins available with this memory. Now if you try to consider a RAM chip, so then the RAM chip should have a chip select, and then you have an internal decoder to decode the particular address. So this is A0 to A0 to A10, right? So these are the address lines, and you can write data into memory or you can read data into memory. So your output data, it has some pins to deliver the output data, and it has some pins to give input data. So here you have input buffer and output buffer, and here you have write bar, and any memory should have this particular pin chip select. When these particular pin, when you are connecting it to 0, then this pin is select, this IC is selected. When the IC is selected, then only you can do memory read operation or memory write operation. That corresponds to what means, that depends upon the internal decoder. And read bar is one more thing. When it is going low, then a byte can be read from memory. And you can write something into memory when write bar is low. So these are related with input buffer and input data pins, and output buffer and output data pins, internal decoder. So these are the details of the memory structure, details of the RAM. And coming to the E square PROM, here using 8086, you can only read. Either you can only read, so there is no input data here or input buffer here. So when processor gives an address A0 to some address, then these address lines depends upon the size of the memory. This we will clearly try to discuss this. And here you have an output buffer. So and when chip select is selected, that particular ROM, PROM is selected when it is 0. And then when you want to read a byte from this, then you will give 0 on this read bar pin, so that the content of E square PROM will come out of this. So this is what the memory structure of RAM and EPROM. Now we need to interface these things to 8086. Now, so coming to the size of the memory, here you have 2048 by 8, and here you have 4096 by 8. So what do you mean by this? This is 4K EPROM, and then this is 2K EPROM. So then similarly you have memories of different size, 1K, 2K, 4K, 8K, 1 MB, or 256K, 128K. So like that you have different sizes of memory chips available in the market. So then how many address lines the memory, or how many address lines the memory chip should have? So if it is a 1K memory location, then you should have 10 address lines. And if you have 2K memory locations, then you have 11. So already in the last class I told you, if you have 10 address lines, then that is of 1K, and if you have 20 address lines, that is of 1M, 1 MB, 1 megabyte locations. If you have 30 address lines, so then that is of 1 giga. Then if you have 40 address lines, then the memory locations can be 1 tera, right? So now if you consider 11, that means 2 power 10, 2, that means 2k is the memory. If the chip is having 11 address lines, then that is having 2048 memory locations. If the memory is of 4k, means that should have 12 address lines. And if the memory is having 13 address lines, then 2 power 10, 2 power 3. So 2 power 3 is 8, so 8k memory locations. And 14 means 16k memory location. 32k means that should have 15 address lines. And if a memory is of 64k means that should have 16 address lines. So this is what the address lines require of 64k. So then you have 128, 256 kilobytes of RAM ICs available. So coming to the memory types, this is PROM, and then this is what we can discuss up to now. So, and coming to the memory, this is more in detail about that. So now how to interface these things is what we'll try to see now. So coming to the dynamic RAM interfacing, okay. See, you have to very clearly know here what we are doing is we are trying to interface memory ICs to 8086. So then what we need to do here is we have to know the hardware detail of this and hardware detail of 8086 processor, and we have to know the hardware details of memory IC. Then only we can connect them, and then only we can say we can interface them, right? So now let us try to see what are the hardware details of memory IC. Okay, and then now let us go ahead. So coming to the DRAM, dynamic RAM IC, if you try to see how to interface this DRAM to 8086s. Now let us try to see in detail. So memory chips are rated by their access times. And what do you mean by this access time? The memory access time is the time from receiving the address to delivering the data. It is very important. When you are designing a system, a programmable system, you can take DRAM or SRAM. But selecting of that one depends upon few parameters like memory access time and then their packing density. So if you try to take memory access time, how to define memory access time? The time taken, okay, the time taken by the memory to receive the address and how much time it takes to place a byte on the data bus. So it is essential to decide whether wait states are needed or how many of them. That means now if you try to see the memory access time, I think somewhere here I think I have written, yeah, this is what the memory access time is. See, the 8086 processor, if it is working with 10 megahertz, then within 100 nanosecond it can give the address. Okay, it can give the addresses, but the memory is not that much fast. So we are defining here memory access time. How memory access time is defined as the time taken by the memory to receive an address. When the processor gives the address, how much time it takes to deliver the data. So then how do you calculate it? That means, if memory access time is in the order of nanosecond, then no problem. But the memory access time of the memory access time is in the order of millisecond. So processor is working with 100. So I'm trying to discuss the memory access time. So the memory access time is the time from receiving the address to delivering the data. Now memory and processor is very fast. It can access data very fast, but memory is very slow. So then the processor has to wait until it has to perform the reading operation. So then how many clock cycles, how many wait cycles need to be introduced by the processor is once the data is available on the data bus, then it can fetch the data. But now as a memory is low performing device, then we need to add wait cycles into the memory read operation. So this is what we have seen in minimum mode of operation is. So when we try to see in the minimum mode of operation, here T1, T2, T3 and T4, if the memory is slow, then what happens is, when memory is slow, then processor places another clock cycle wait cycles. Until the data is ready on the data bus, it introduces a wait cycles. See very clearly, when processor is doing memory read operation or IO read operation, if IO devices, if they are slow, if they are fast enough, then no problem. If they are not fast enough, then the processor will introduce wait cycles into the memory read cycle. So how many wait cycles need to be introduced is what we are trying to calculate now. Right. So now if you try to see here in DRAM interfacing, to have no wait states means what? The processor access time should be greater than the memory access time. So P for the processor and M for the memory. Otherwise, wait states should be added. So how many number of wait states should be added? So processor access time and memory access time should be given by the manufacturer. So the processor access time is clock dependent. It means 8086 is working with 5 megahertz or 10 megahertz, the access time varies. So from this, we can see that the memory access time, that means processor takes 2.3 T states, okay, 2.3 T states for 8086 and 1.0 T states for the other processors. So now 8086 based systems, if you consider, the processor takes 2.3 T states, means first, second, means 2 clock cycles and 0.3 T states. So now if you consider this here, the bus cycle timing of 8086, each bicycle is of 4 T states. Bus cycle, each bus cycle is of 4 T states, T1, T2, T3 and T4. And the memory read, that means a byte reading from the memory, the processor 8086 will take 2.3 T states. Now address lines, if you consider here, the memory read cycle, when it is given, then first cycle, second cycle, and then the data is available at third clock cycle. Here if you try to see, so here if you try to see the timing diagrams, now the data is available at this clock cycle is 2.3 T. So here, now that is what you can see here. So now we can say that the amount of access time allowed by the memory is 3 clock periods minus the address setup time minus the data setup time. So the processor time is 3 clock cycles minus the 3 clocking periods minus the address setup time. Okay, then so it is given that when F is 5 megahertz and this should be mentioned by the manufacturer. TCLAV. TCLAV is the address setup time and then the data setup time. That means, when the processor gives the address, the memory address need to be, activated, and from that a byte has to be fetched on the data bus. So that is the data setup time, TDVCL, and this is address setup time is TCLAV. So then the processor access time is 3 clock cycles minus this time minus this time. So TCLAV is 100 nanoseconds and TDLAV is 30 nanoseconds. Then processor access time is 3 clock cycles minus this time means 460 nanoseconds. Within 416 nanoseconds, the processor can access a byte. But memory is not that much fast. So for 8086, the TCLV is 55% of the clock period, and TDLV is 15% of the clock period is what we are considering here. So this 3T minus 0.55T and 0.15T. So which is of 3T minus 0.7T, which is of 2.3T cycles. Okay, so this is what the generalized, how you got this 2.3 is what we are trying to see here. Okay, this is about the processor access time. And for various processors, the access times are this way. 8086, if it is working with 10 megahertz, then each T state is of 100 nanosecond. Then the access time is 2.3, 230 nanoseconds is what you can consider this. Okay, each T state is of this much. But whereas 80386 and 486, where there are more number of pipelines are incorporated, then the memory access time would be 45 nanoseconds or 30 nanoseconds itself. So now you can see Pentium 4, if it is working with 530 megahertz, then 2 nanoseconds it can access the memory and can fetch a byte if it is given. Right, so then memory is not that much fast. So then how many number of wait states need to be added into the read cycles? So now if you try to see the access time, then the difference time is T access memory minus T access of the processor. That those many number of cycles the processor has to be waited. So the memory access time, so the number of wait states is T difference by T. Okay, so then if you take an example, if the processor crystal is of 24 megahertz, then the memory access time is 440 nanoseconds. Then determine the number of wait states to be inserted into the bus cycle. So then the processor clock frequency is 8 megahertz. Right, this is what the crystal frequency. Right, so by 3 is what you get. By 8284, then 8 megahertz is the clock frequency you get. Then the processor clock period is 8 megahertz means 125 nanosecond. Then the memory access time is what 2.3 clock cycles is what we have seen. So 2.3 into 125 means 287.5 nanosecond. So then the memory access time is larger than the processor access time. That means 440 nanoseconds. Right, the memory access time is 440 nanoseconds. So then, but the processor can fetch the data within 280.5 nanoseconds. Then the wait states need to be inserted. So then the wait states would be 440 minus 287.5 by 125, which is of 1.22, means roughly 2 wait states need to be required. This is very, very important. See here, now you are, I just try to conclude. Here now if you try to see, like when a processor is performing a memory read operation, then memory is not as fast as the processor. Then how many number of wait states need to be introduced is what we are trying to discuss. Now, the example which we have taken is, if the processor is working, that means, if the crystal frequency is 12, then divided by 3 is what we get. So 8 megahertz is what the clock frequency is. And then the processor clock period is 125 nanosecond. And processor access time is 2.3 clock cycle for 8086. So 2.3 into 125, that is 287.5 nanosecond. Means processor can access the memory within 287.5 nanosecond. But as the memory access time here is 440 nanoseconds, means when the moment the processor gives an address, it takes 440 nanoseconds to react and give the data on the data bus, which is also very fast, 440 nanoseconds. So then 440 minus 287.5 by 125. That means it is close to 1.22 times. So 1.22 means two wait states need to be added here. So if it is now, like, this is what you have to understand. When memory is slow, processor is fast. So then the processor will go into wait states until the data available on the data buses. So here two states need to be added. So this is what the timing diagram. When a slow memory of 440 nanoseconds access time, if it is connected to a processor, then the processor has to be waited. This is what the memory and then memory number of wait states you need to add. Okay, right. So coming to now, this is what the number of wait states need to be added calculations. Now let us try to see dynamic RAM. So whenever a large capacity memory is required in a microprocessor system, the memory subsystem is generally designed using dynamic RAM because there are various advantages of dynamic RAM. So higher packing density of DRAM, okay, more memory available in less space, lower cost and less power consumption. And but the disadvantage of this DRAM is you have to refreshing for each clock cycle. You have to refresh the memory. So instead we can go for SRAM, static RAM. So static RAM is manufactured using transistors. DRAM is by using capacitors, right? So these are the DRAM cell and how they look like. Then you have a row decoder and a column decoder and data buffer, input data buffer and output data buffer into a memory is. So now let us try to see how to connect this dynamic RAM. This is about interfacing dynamic RAM. So when you are interfacing dynamic RAM, you have to multiplex the two halves of the data cycle, okay, and refresh each time. And this is what has to be done. But now let me show you the DRAM and DRAM details which are available in the market. So memory interfacing, now if you try to see, yeah, so these are the things we have seen up to now. So yes, now HY62256 is a Hyundai made memory IC. So this memory IC now need to be connected, interfaced to 8086 processors. So now if you see here, HY62256, this also you can find it in the lab of your microprocessor kit. A0, A1, A2, A3, A4, A5, A6, A7 and A8, A9, A10 and A11, A12, A13 and A14. A14. So that means how many address lines are there? A0 to A14 means 15 address lines are there. 15 address lines, when 15 address lines are there, then what would be the memory size of it. So 2 power 10, 2 power 5. So this is 32K. 2 power 5 is 32 and 15 only. Here we have A0 15 only, A14 only. So A0 to A14 means this is 32K. So this memory is of size 32K. It has 15 address lines. So it is a 32K, means 32,000 locations are there. Each location can store 8 bits of data. And input and output data lines 1, 2, 3, 4, 5, 6, 7, 8. So this you can read a byte from the memory using these lines. Okay, so then here you have output enable, because from the buffer you have to bring into the data bus. So output enable and write enable, and this is what the chip select is. So this chip select, when it when it is 0, then this memory IC is selected or enabled. So this is chip select pin. So output enabled, write enable, and read. So this is what HY62256 IC is. Okay, so write enable, output enable, writing into it or reading into it. Reading into it means you have to give this a pulse on this output enable, output buffer is. This is what the pin diagram or pin description of the memory IC. Now if you try to see the block diagram of it, it has A0 to A14. Coming to the control logic, you have 3 control signals: chip select, output enable, and write enable. Okay, and a byte you can fetch at each time. So here you have an output buffer. Okay, right. So these are the ratings, maximum voltage which you can connect, and minimum logic levels, TTL and all. When you try to see the input VIH and VIL, you can try to see. So this is what the timing diagram of this particular IC given by manufacturer Hyundai. This is a Hyundai made IC. So now when these control signals are, when chip select, if it is high, then it is in standby mode. That means that is at high impedance states. The data lines are at high impedance state. So if you want to perform a read or write operation, then chip select should be low. When it is low and write enable is high and output enable is high, and then output is disabled. In this case also it is at high impedance states. And when it is low and then output enable is low, then you can perform a read operation. And when it is low and write operation, when it is low and then whatever it is here, it is don't care, then you can do a write operation. Okay, so this is what the write cycle, where your output enable is locked in this particular IC. So now let us try to see a RAM IC and ROM IC of 4K by 8 and 32K by 8. So now if you see a RAM IC, this is of D0 to D7 and A0 to A11. So this is 4K by 8 RAM, and then this is what we bring in. So you have to be very careful. Here, I have shown you the complete details of the memory IC HY62256 Hyundai IC. This is what is there in your electro systems made 8086 kit. So that's why I am showing it. So here the moment it is, you want to interface this. So then this is what we are trying to see: RAM A0 to A11, and then you have output enable, write enable, and here you have chip select, and then here you have the data lines, and then here you have the address lines. And now coming to the DRAM interfacing, when you try to see, for 8086 based systems you need 2 memory ICs. This we discussed very clearly in memory segmentation. The memory of 8086 is divided into two because 8086 has 16 data lines. It can take 16 data bytes at a time into the processor. But if you use only one memory IC, it takes two clock cycles. So it is wasting in a clock cycle. So then what we do, we divided the memory into two bands, even band and odd band. Right. So then when we do memory interfacing, two memory chips are needed. Right. So then each memory has address lines. Each memory is of data lines. It's a byte is what we are saying. 4K by 8 means 4 kilobytes memory. So each memory has data lines. Okay, each memory has data lines. So now this is what the fundamental thing you have to know when you are interfacing memory to the microprocessor. So this is your even band and this is your odd band. So what we do, the address lines of this and the address lines of this A1 to A19, we will give it to A1 to A19 of the processor. So interfacing means how you are connecting, you should know. So the A1 to A19 and A1 to A19, if you have a 1 MB means total 1 MB locations, if you try to see, then D0 to D7 of 8086 should be connected to the lower band means even, and D to D15 should be connected to odd band. So this is a rough sketch you should know in the mind. That means here D0 to D7 of this memory should be connected to D0 to D7 of the processor. And D8 to D15 you have to connect it to the upper band, odd band. And two signals we use very clearly. One is bus high enable and another one is A0. A0 is connected to chip select of the even band and bus high enable is connected to chip select of odd band. This is fundamental. So your A0 pin and BHE pin are connected to, see here you have chip select of each memory IC. So A0 of microprocessor you connected to chip select of this RAM and BHE of microprocessor you connected to chip select of the odd band. So even band and odd band selection is done by using these two particular pins A0 to BHE. And now this address lines A1 to A19 and this address lines A1 to A19, you can give it to address decoder. You can connect in between address decoder to identify based on the memory mapping which address you can use address decoders. But this is the fundamental memory interfacing concepts. Is it all right? So now if you try to see a decoder, so then see here we have seen the fundamental things here, like what happens when you are doing memory interfacing, which lines has to be connected to which lines, which pins of 8086. So a rough sketch we have seen, data lines we have seen, address lines, chip A0 we have seen, BHE we have seen. So here it is an address decoder for 8088. 8088 is a 16-bit processor, but it has 8 data lines. That is only the difference. It has an ALU of 16-bit, but in the beginning when computer is designed, 8086 based computer, if it is designed, 2 memory chips are needed, but memory is very costly. Now if you try to see a computer, the first costlier item in your computer is processor, the second costlier item is memory. The moment you go to your market and ask, I need a computer based on i3 or i5, then some cost. Then let us say you fixed your processor, then I need a memory of 4 GB and 8 GB. Then cost would be 3 to 4,000. So in the beginning, memories are very costly. So then to design a commercial system, what they did is they brought one more processor called 8088, which has only 8 data lines. That means only one memory is needed to design a system, but system performance is slow. Right. So now one such system I am showing here, which is how to design a decoder in between. See here, in this case directly A1 to A19 we connected A1 to A19, but like that particular RAM should be connected to 2000H. That means the RAM which you interface should have this address, means we need a memory decoder, or sorry, we need an address decoder. So now here, this is an example how 8086 base system it is connected. So it is a 64K by 8 memory IC. So 64K means you should have 16 address lines, A0 to A15. So 2 power 6, 2 power 10, so 64K. And A0 to A15 of the memory IC are connected to address bus of your 8086. And D0 to D7 of the memory is connected to D0 to D7 of 8088. And A0 to A15 of memory has to be connected to anyhow here you have only one memory IC, then A0 to A15 you can connect, but A16 to A19 are used to select, or you are connected. See here, A16 to A19 are given to a decoder by which you can select this memory ICs. That is what the difference is. And here you have memory write operation or memory read operation, that I0 by M bar and your read bar and write bar in combination that generates this particular signal, say a memory write or memory read are connected to write enable or output enable. Okay, so here is what we need, a decoder IC. That means when processor gives A16 or A19, then that is used to select that particular chip. So then how to design this decoder is what now need to be seen. So this is 8088 where only one, that means the processor has only one data line. Now you consider 8086 address decoder. It's very important. Any RAM IC, if it is given to you, this is how you have to connect. So memory interfacing is what? Connecting in a compatible manner. So one pin of memory you are connecting it to one pin of your processor, but that with the help of that means some compatible things in a compatible manner you are connecting. So we are needing here a decoder. So now it's very important. Now let us try to see how to, so this if you understand, then you can, off the way you can interface memory to the processor when you are designing a system based on 8086. If you understand this, your I3, I5 and all is very easy. Now I have 64 by 8, 64K, that means 64 kilobytes of memory, 64 kilobytes of memory. So two memory ICs are needed for 8086 because we are dividing the whole memory into even bank and odd bank. Because 8086 has how many data lines? 16 data lines. So lower byte is connected to D0 to D7 of the processor data lines. And D0 to D7 of the odd memory line is connected to D8 to D15 of the microprocessor. And here, carefully if you observe, here you have an arrow mark here, here you have an arrow mark here, means data lines are bidirectional. So this is, bidirectional. The data can be fetched from the memory to the processor, or the data can be written into the memory. So it is bidirectional. This sign is of bidirectional. So if you consider a memory IC, then here The data lines of this is connected to the data lines of this D0 to D7 and D8 to D15. And the even bank chip select is connected to A0. This is connected to A0. And that odd bank chip select is connected to bus high enable from the microprocessor. All right. Okay. And now A0 is when A0 is for allocated for selecting this even bank. Then the address lines here A0 to A15 means 16. So A1 to A16 address lines of the processor are connected to A0 to A15 of the memory. Same thing with here also. This is 64K, then this is of 64K. Right. So then 16 address lines are here, 16 address lines are here. So then we need 16 address lines of the processor, not A0. Be careful here, not A0, because A0 we are using to select even bank and BHE we are using to select odd bank. So A0 is not, we are not using here. So A1 to A16 is what we are connecting it to microprocessors. And what happens to the rest of the pins? A17, A18 and A19. So A17 and A18 and A19 in combination with A0, right, and BHE. If you are doing a byte operation, then this bank can be selected, or word operation, both can be selected. So they are used to decode chip selectors. So here now if you try to see the address decoder, so now this address decoders can be any logic you can use here. The address decoder you can use anything here. So this is what you can keep in mind when you do interfacing, memory interfacing. This is what the basic fundamental connections you have to make. So I came from a very fundamental point, like I introduced a memory IC to you. What is the content of memory IC I have seen, then from that how to interface this with 8086 processor and 8088 processor is what we have seen. Now we need to do memory mapping, means what? Interface a RAM IC so that my segment, my code segment can have 2000 code segment and data segment. So that means if a question is, or if you want to design a system so that code segment can start with 10000H is what the thing you need to do. So then the fundamental connections are this, right? So code segment and data segment can overlap because 64K. So within a segment you can define these two. That is what done in the lab trainer field. Just observe. So now how to, that means I have to define my code segment 10000H. So then how can I define it? So that means I have to design a decoder. So this decoder can be of simple gates, it can be of block decoders, it can be of PLAs, it can be of EEPROMs. Now let us try to design this. So when you are using simple NAND gate, okay, simple NAND gate, that means what? These memories should be given an address of 10000H. That means when it is 100H, see here it has 64,000 locations. So this memory location should be given an address of 10000, and this address would be 1001. This is odd address. So there are 64,000 locations are here, 64,000 locations are here. So then the next address will be 10002, the next address will be 10003. So these are all odd addresses in one bank, even addresses in this bank. So now, how should I, that means when address is even, a byte should be fetched from this. When address is an odd, then byte will be fetched from this. If it is a odd operation, starting with even address, then a byte should come from this, a byte should come from this, then 16 bits can be read by the microprocessor. This is what need to be done. So then you need to go for memory mapping. So then you can use simple gates. Right, so this here is one an example, is what I mentioned now. Design a decoder for 8086 SRAM memory interface for the figure shown such that the memory is mapped to the address range 0002 1FFFFH. This is what the problem is. Listen carefully. This is what the example is. Design a decoder for 8086. That means here, how to make connection I clearly explained. Now, this decoder should respond, should identify a memory location when this is the cases. So now if you try to see here A17, A18 and A19. Here you try to see A17, A18 and A19 are given to a decoder. So decoder can be a simple OR gate. So this is one a simple OR gate if you try to see here. Right, so when it is 0, 0, 0, then output is 0, memory, no, output is 0. So output is 0 means when it is 0 and when it is 0, this bank is 0. That means here it is 0. This is a simple OR gate. Okay, so then this particular thing is selected. So when it is even, address, then this is what can be selected. And when it is odd, right, so this is a simple OR gate. You can say that when it is 10000 and 1FFF, those things can be identified. So now if you consider this address 00000 corresponds to this, and 1FFF, 1FFF. So now this is like A19, A18, A17, and anyhow this A16 is connected there only. So now here if you try to see A17, A18 and A19, and when they are all 0, right, when they are all 0, so when they are all 0, if you have an OR gate here, the output is 0. So that is what the OR gate you can design here. So decoder can be designed by using a simple IC. So you notice that the user address lines are A17, unused address lines are A17 to A19, so they must always be low. So they must be always low means what? We need a simple OR gate here. Okay, so this is how the memory interfacing is done. So here in this class what I discussed is, I have discussed in the beginning very clearly what exactly is the maximum mode of interfacing. So in maximum mode of interfacing, we need to generate different control signals. Then those control signals can be generated by using 8288.